Welcome to the GATEsolution Academy. Today we are going to study strain energy stored, strain energy stored in a body when load is applied suddenly. All right. Let's see how this works. We all know that when the load is applied suddenly to a body, the load is constant throughout the process of the deformation of the body. Just consider a bar. We'll consider a bar subjected to sudden load, right? And we have already said that the load is constant. So let's define some of the terms, right? Let we say P, that is the load applied, suddenly, right? L, that is defined as the length of the bar. A is area of the cross section. V, that is the volume of the bar, which is also to be written as area into length. E, we all know that it is Young's modulus. And X, that is the extension of the bar. Extension of the bar due to load P. Sigma, that is its stress induced. Stress induced by the suddenly applied load, and U, obviously the stored strain energy. We can define as strain energy stored, right? Now, as the load is applied suddenly, the load P is constant when the extension of the bar takes place. Therefore, work done by the load is equal to the load into extension. That is load is defined as P, extension is defined as X, right? So based on this observation, the maximum strain energy is stored. You want to write the maximum strain energy is stored, that is the energy. If we want to know what is maximum strain energy, it means that the energy is stored up to elastic limit, right? And this maximum energy stored in the body is given as U is equals to sigma square by 2e into volume of the body, right? Now let's see, equating the strain energy stored in the body to the work done. We get, this is the volume of the body, and we have already discussed the volume of the body is defined as A cross L. So these equations can be written as sigma square by 2e into volume, that is A cross L, and this is also equals to the work done by the load, that is P cross X. Now load into extension can also be written as P into extension, that is defined as sigma by E into L, right? So we can see that this sigma, and this square of the term is cancelled out. This L, and this E, and this E is also cancel out, and we'll get P, that is the load. P is defined as, the value of P is defined as sigma by 2 into A, right? Or the sigma can also be written as twice of P by A. From the above equation, it is clear that the maximum stress induced due to suddenly applied load is the stress induced when the load is applied gradually. It means what? The sigma is defined as twice of sigma gradual, and this is defined as suddenly applied load. Therefore, we can conclude that when strain energy is stored in a body due to load is applied suddenly, the stress developed in that body is twice the stress developed in a case of gradual applied stress. So let's take one example, and based on this we'll solve, right? So in this, let's take an example. In this case, a tensile load of 60 kilonewton is gradually applied to a circular bar of 4 centimeter diameter and 5 meter long. If the value of E is equals to 2 cross 10 to the power 5 Newton per mm square, determine first part, that is stretch in the rod. Stretch in the rod. The second one, stress in the rod. And the third part, strain energy absorbed, strain energy absorbed by the So let's see how this question is going to be solved, right? So this is the case of, let's first understand this is the solution, and in this solution we already defined that it is a gradually, this is a gradually applied load conditions, right? In a tensile load of 60 kilonewtons is gradually applied. So based on this, let's understand this is we can say the load is of 60 kilonewton, which is to be defined as 60 into 10 to the power 3 newton, right? Diameter of rod is given as 4 centimeter, that is a 4 centimeter, which is also to be defined as 40 millimeter, right? Therefore area, if you want to find out the area, then area is to be defined as pi by 4 into diameter, that is your 40 square, which is also to be written as 400 pi mm square. Length of the rod is given as 5 meter, which is to be defined as, in terms of millimeter, it is to be 5000 millimeter. Therefore, let's first find out the volume of the rod, right? So when we're talking about the volume of the rod, we need area into length, that is A cross L, which is defined as 400 pi into 5000, which is equals to, that is 2 into 10 to the power 6 pi mm cube, right? In this question, Young's modulus, that is E, is given as 2 into 10 to the power 5 Newton per mm square. So we need to find first what is the stretch in the rod, right? So X, that is the stretch in the rod is defined as X, and this X is also to be written as X if we want to find the value of X. So X is what? That is the extension in the rod, or you also can say that the stretch in the extension in the rod, right? So that extension, that X, the value of X is defined as sigma by E into L. Now, from where this equation comes, let's see this. We know that the strain is defined as change in length X upon original length, right? So the value of X is defined as epsilon into L, right? And we all know that up to elastic limit, stress is directly proportional to strain. That is, if it follows Hooke's law, stress is Young's modulus into epsilon. Therefore, this equation epsilon is also to be written as sigma by E, and you can replace this values of epsilon by sigma by E in this expression, and you will get this value, right? Now here in this case, the value of L is given, E is given, sigma. So sigma is defined as load per unit area. Load is already given as 60 kilonewton. Area you have already calculated. So based on this, you will get this expression. So let's put all the values in one place. The values of sigma, that is P by A. So the value of P by A can be written as 60,000 upon area, that is you can say 400 pi into the value of E is defined as 2 into 10 to the power 5, and that is the length. That is the length is defined as 5 thousandths. All unit comes in millimeter, and this equation is defined as 1.19 mm. Right? So you have already calculated the value of x, which is come as 1.19 mm. The first part we have already calculated, that is the stretch in the rod. The second one, the stress, right? The sigma, the stress in the rod, and you have already defined the sigma, that is stress of the rod, sigma, right? So we can say that in the continuation in the next slide, we can say that the sigma, that is the stress in a rod, is defined as load upon area, right? Which is also defined as P by A. The value of P is defined as 6000 by 400 pi, which is also defined as 47.746 Newton per mm square, right? So in the previous one, your answer of the stress in the rod is given as 47.746 Newton per mm square, right? The last part, that is the strain energy absorbed by the rod, right? The third one, the strain energy, right? So how much strain energy is absorbed in the body? It is to be defined as it is represent U, and the strain energy is defined as sigma square by 2E into this volume of the rod, right? So we all know that the value of sigma is defined as 47.746 of whole square upon 2 into, that is the value of this E, 2 into 10 to the power 5 into, that is the volume. Volume is already we have calculated, that is 2 into 10 to the power 6, 5, right? So all when you calculate this expression, you will get the strain energy, that is 35810 Newton mm, right? In terms of Newton meter, this value is written as 35 when you, because it is in mm, so we divide it by 1000, so we'll get 35.81 Newton meter, right? So strain energy stored in the body is 35.81, so we can simply write it in here. The answer of strain energy is defined as 35.81 Newton meter, right? So this is a case when you have a gradually applied load, right? So let's understand, if we have a tensile load. Suppose in this question, if we introduce, there is a modification, and if we say that a load of 60 kilonewton is applied suddenly, determine first maximum instantaneous stress induced. That is the first part. Second part is instantaneous elongation. In the rod. And the third part, what should be the strain, what should be the strain energy absorbed in the rod, strain energy absorbed in the rod, right? In the previous question, we have seen the load is of 60 kilonewtons gradually applied, but in this question, if we apply, rest of the data is same, but if we applied load of 60 kilonewtons and suddenly applied, then how we are going to find all these values, right? So let's see one by one equations. We all know that this is the solution, and we all know that area we have got already calculated as 400 pi mm square. Length we have already defined is of 5000 millimeter, and volume we have defined that is 2 into 10 to the power 6 pi mm cube, right? E in the expression it is given that 2 into 10 to the power 5 Newton per mm square. And yes, there is a change of 60 kilonewton, but that load is applied suddenly. So we give this P value, PS, which is to be defined as, and this is defined as of 6,000, 60,000 Newton, right? So the first thing, the first part, we are going to calculate, we are utilizing this space, right? The first part that we are going to solve is a maximum instantaneous stress induced. And we all know that the maximum instantaneous stress induced in a body when a load is applied suddenly is twice the load applied by a gradual. So here P by A is a gradual, so we can define it 2 into 60,000 divided by 400 pi, right? It means what? The gradual applied load, uh, the stress induced when you have a suddenly applied load is equals to 95.493 Newton per mm square, right? Now the second part that we are going to see is the instantaneous elongations in the rod, right? So let's suppose that is x is defined as the instantaneous elongation. Instantaneous elongation, right? When we say that x is an instantaneous elongation, then x that we have already defined is sigma by E into L, right? The value of sigma, it means the stress, instantaneous stress on the basis of instantaneous stress. The elongation is, instantaneous elongation is there, right? So we have already calculated the value of sigma s, which is defined as 95.493 upon the value of E, where it is already given in the question, that is 2 into 10 to the power 5, and the length, that is of 5,000, right? So the instantaneous length x, the value is defined as 2.38 m. That is the second part of the question. This is the first part of the question. Now let's see the third part. How much strain energy stored in the body? And we all know that the value of the strain energy stored in the body is defined as sigma square by 2e into volume, right? So whatever in this question, we know that the strain energy is directly proportional to stress, and if this stress is suddenly applied load, then this value is defined as 95.493 0.493 of whole square into volume, that is 2 into 10 to the power 6 of 5 divided by 2 into 2 into 10 to the power 5, right? So the values of U come as 1, 3, 2, 3, 8 Newton M, right? And in Newton meter, this value is 143.238 Newton meter. So class, you can see that when you apply a load of 60 kilonewtons, a suddenly applied load, you will feel that the extension is 2.38 mm, right? And when you compare it with the previous case, when you have a load of 60 kilonewton which is gradually applied, the extension is 1.19. It means what? Yes, the stress is doubled in this case. So based on this, your extension should also be increased. Now let's see what will happen when strain energy is stored in a body and the load is applied with impact, right? The next topic that we are going to discuss is strain energy. You can say that strain energy is stored in a body when the load is applied with impact, right? So let's first understand what does the impact means, right? Let's draw a diagram, and here in this rod with a collar is connected, right? And suppose there is a load which is at this particular height. You can say this is a load, right, which is at a distance of h, and this is a collar. So when this load hits on this collar, there is definitely some extension, right? And if we have an extension, we can say that this is your extensional length, that is delta. This is the rod of the L is defined as the length of the rod, right? That is load we have already defined P. So the load drop, that is load applied with impact. So what will happen? Let's see. The load dropped from a certain height before the load commenced to stretch the bar is a case of load applied with impact, right? So consider a vertical rod fixed at the upper end. This is fixed at the upper end and having a collar at the lower end as shown in the figure, right? Let the load be dropped from a height on the collar. Due to this impact load, there will be some extension in the rod, and that extension is given as delta L, right? Now, here in this case, L, that is defined as the length of the rod, area cross sectional area, volume of the rod is given as A cross L, H is defined as the height through which load is dropped. Delta L, that is the extension of the rod due to load P, and E is the modulus. The important thing to write here in this case is sigma, right? What is sigma? That is the stress induced in the rod, the stress induced in the rod due to impact, due to impact load, right? So let's see. So the strain in the bar is given by, we can write the strain. So how much strain is to be developed in this one? It is to be written as stress upon. So this is to be written as, what is the strain? We can say that change in length, that is delta L by the original length, is equals to sigma by E. Or we can also define as delta L is sigma by E into L, right? Therefore, work done by the load, how much amount of work is to be absorbed, or you can say the energy absorbed, is defined as work done by the load, right? So work done by the load is defined as load into distance moved, right? So it means what? Load is defined as Q, right? And how much distance is moved? H distance plus delta L, right? So this is the total distance moved. Based on this, the strain energy stored is strain energy stored by the rod is given as U is equals to sigma square by 2E into, that is volume. So we can also written as sigma square by 2E into area into length, right? So we all know that when I say the stored energy stored in the body, that is equals to the work done by the load, right? So we can write this expression, that is P H plus delta L, which is also equals to sigma square by 2E into area into length, right? So when we equate this, delta L can also be written as what? Sigma by E, that is P H plus sigma by E into L, which is also defined as sigma square by 2E into A into length, right? Now we just simplify this equation. We can write P into H plus P into sigma by E into L, which is also defined as sigma square by 2E into A into L, right? Now moving to the next slide, we'll elaborate this equation in a simplified way. We can write it like sigma square by 2E into AL minus P into sigma by EL minus PH is equals to this. Now this equation, in this equation, multiply by 2E by AL to both sides. We can write multiply by 2E upon AL in both sides, right? What we will get when we multiply with this equation? We will get sigma square minus this A by 2, AL by 2E is cancelled out in this expression. We will get P dot sigma by EL into 2E by AL minus PH 2E by AL equals to 0. Now you can see that this E is cancelled out in this conditions, right? L is also to be cancelled out, and you can find out this expression to be written as sigma square minus 2P by A sigma minus 2P E H upon AL is equals to 0. Now you can see that this is a quadratic equation, and based on this quadratic equation you can find that sigma has two values, right? So we can simply write this quadratic equation, and if you want to find the roots you can write that sigma is equal to 2p by a plus minus under root of 2p by a of whole square plus 4 into 2p h by a cross l upon 2 into 1, right? So this how we obtain this value. We know that this root is to be find out with the help of b square plus minus under root 4ac on 2a. Now when we solve this expression, we just neglect the root in the negative side. So simply we neglect negative roots, and we simply write sigma is defined as p by a plus by a under root 1 plus 2a eh upon p cross l, which is also to be written as sigma is equals to, you can take it, the value of p by a is common, that is 1 plus under root 1 plus 2a eh by p cross l, right? After knowing the value of sigma, the strain energy can be obtained, right? Now from this expression, we are going to give some important conclusions, right? So that is the important conclusions to find as, you can see that you can obtain the value of sigma from this expression, right? And based on this, you can obtain some conclusion, and that conclusion is first part. If delta L is very small, suppose if delta L is very small, right, in comparison with H. So the load we have already defined, if the delta L is very small, right? So the load is defined as P into H, right? So we can say that the work done by the load is P cross H, right? So equating the work done by the load to the strain energy stored in the rod, we know that now this is P cross H is defined as what? Sigma square upon 2E into AL, right? And based on this, we can define sigma square is equals to 2EPH by AL. It means what? If you under root this, if you remove this square term and implement a under root here, so we can get the value of sigma here in this case, right? Case 2. This is the first conclusion we have defined. Case 2. If h is equals to 0, when you put the value of h is equals to 0, so in this expression, what is the value of sigma? When we apply put h is equals to 0, this whole term becomes 0, under root 1 is equals to 1, and this value is defined as sigma is defined as p by a 1 plus under root 1 plus 0, which is also to be defined as 2p by a, right? It means what? This is a case of suddenly applied load, right? Once the stress is known, the corresponding instantaneous extension delta L and the strain energy can be obtained. So this is all about the strain energy. We have covered in this slide strain energy stored when you applied a suddenly load as well as when you applied a impact load. Thank you. So let's take one example, right? And in this example, let's see how this is going to be worked, right? In this questions, a weight of 10 kilonewton, weight of 10 kilonewton falls by 30 mm on a collar that is rigidly attached to a vertical bar 4 meter long and 1000 millimeter square in section, right? Find the instantaneous expansion of the bar, expansion of the bar. Now take the value of E is defined as 210 G Pascal, right? So let's solve this question. You need to find out the instantaneous expansion, or you can say the extensions, when a load or weight of 10 kilonewton fall by a 30 mm on a collar, right? So let's simplify the term plus, that is 10 kilonewton, that is defined as 10,000 Newton. Fall is of 30 mm, right? Length of the rod is defined as a 4 meter, which is also to be written as 4000 millimeter, and your cross-sectional area is already given as 1000 mm square, right? E, that is the Young's modulus, is defined as a 210 GPa. It means what? 210 into 10 to the power 9 Newton per meter square, right? So E is defined as 210 Newton, 10 to the power this one, and which is also to be written as 210 into 10 to the power 5 Newton per mm square. Now let delta L is defined as the instantaneous elongation, right? We can say that this is defined as instantaneous elongation due to falling waves, right? Okay. And when we have a delta L elongation due to falling of waves, So there must be instantaneous stress is also to be developed, right? Let's use this previous equation. We have already defined the value of sigma. So based on this, we have defined, I'm going to use this expression, that is sigma is equals to, that is P by A under root 1 plus 2EAH by PL, right? So sigma is defined, we have already calculated, that is of 10,000, right? Area we have already calculated is of 1,000. 1 plus under root, that is 2. E is we have already defined, that is student, just please correct me, that is, it is not 210, it is 2.1 when we convert it into Newton per mm square, right? 2.1. So we just simply write it here is 2.1 into 10 to the power 5 into area is 1000 into h, that is of 30, right? Upon p, p is defined as a 10,000 into length, that is of 4 meter, which is equal to 4,000, right? So when you solve, you will get 10 1 plus under root 1 plus 315, right? Which is also to be written as 10 1 plus under root 360, right? Now once you solve this equation, you will get the value of sigma is 187.7 Newton per mm square, right? Now based on this question, you have already calculated the instantaneous stress. This is the value of instantaneous stress which is developed due to the falling of weight, and you have already calculated with the help of this equations, right? Now once you know the value of this one, you can find out, that is E, you know it's defined as stress upon strain, that is sigma upon epsilon. This is defined as, epsilon is defined and strain is defined as delta L by L. It means what? Your delta L expression can be defined as sigma by E into L. Now, the value of this sigma, you can say, is already calculated here. E is given, L is given. So the extension in length, that is delta, that is defined as 187.7 into 4,000 upon 2.1 into 10 to the power 5, which is also to be written as 3.575 millimeter. So this is the answer, or you can say this is the extension in the length due to impact load. So in this portion we have covered the two things, that is strain energy stored by suddenly applied load as well as strain energy stored by impact load conditions. Thank you so much.